This slide is a combination of all the factors involved in HVAC decarbonization for the 2050 grid. We're going to build this slide very quickly in sequence here and try to help you see what all the pieces are. This is part of a much larger presentation you can find a link to in the description under the video. First, we have the basics here. We have these different types of heating systems across the bottom. These are all heat pumps going from geothermal to air source. Of course, we have geothermal, which you all know what they are. VRF and air source are two different grades and qualities of air source heat pumps. First off, all this fossil stuff is just not a zero carbon solution at all, so it has an infinite time to get decarbonized. This line shows the installation cost roughly, though right now we have IR tax credits, so it's that. And then the other line shows operational costs to some degree. So giving an example for geothermal, this is where that ground loop is running on an example of this ASHRAE building study that Xiaobing Liu and Jeff Spittler did. And knowing Atlanta, I know this thing should be down here around the average temperature for Atlanta, so that would be better. Of course, that's what the CGD teaches, how to do this with more sophisticated stuff. Listen to the longer thing. The bottom line is it's an annual cycle thermal battery. So GHP, consider this no thermal battery on the air source, an annual cycle thermal battery for the geothermal heat pumps. Again, cost is a lot less than it shows. Looking at the details from that study, you can see the cost of the power by temperature at the summer and winter peaks for the VRF and the air source heat pump. And there I installed what this loop should be running if done right. Considering the basic air source heat pump code minimum solution, that thing will jump up with electric strip below anything like 25 or 30 degrees and create a point that we're just never going to build a grid for. So that's why those aren't here. But even when you consider these two, it's a 2-to-1 relationship roughly on cost to operate at the peak, but it's a lot more than 2-to-1 when you consider the type of batteries involved. So you got to take this all into account when understanding these systems. And so this air source heat pump, again, that's coefficient for 1. Again, not a zero carbon solution at all. Never happened. There's the coefficient performance for these others that we understand. Next step, consider this study done in Canada on how much it was going to cost to build out an electrified grid with geothermal versus air source heat pumps. And you can see they came up with basically a 2-to-1-ish cost ratio for air source heat pumps versus geothermal. And that puts us these kind of points up here. None of this is to scale. So, just try to take it in. Our point is that there's another class in here of batteries, another class of something that we believe will produce this kind of a cost curve overall for the transition, thus affect the speed to decarbonization. Now, there's another factor involved in 2050, and that is the cost of power. There's a wind power, and notice it's wildly fluctuating. Even if you consider some base load, there's wild 0 points in there. And then even within the day it fluctuates. Solar, of course, is just as bad or even way worse. And interestingly, by the time we get to 2050, we will have built more than enough solar, even at winter peaks, to make the system all work well. So there's going to be a lot of very inexpensive power available. Already, you can see this is the exact same time shot. You can see there's wild power fluctuation costs. Looking at some real data, even as old as 2009, you can see these negative costs for power in the areas where there's a lot of wind, and this much more recent graph showing negative cost for power in entire regions. So this is where this is going. And while it may not be zeros on the future grid, there'll be more better rents, better managed. It will be wildly varying in cost. And so that is part of this paradigm. So in this other area, basically we've got water tanks. People have been using these for a long time, shifting power from the lower cost at night, the day before, to the afternoon in the summer. But that's a day battery. Let's tie just those points back to the study we did of Asheville load. This is a real load example. Actual peak load with the residential on top in Asheville on a certain winter peak. That's what the growth is going to be like here. Notice the growth in the country is going to be roughly 3 times what this growth is projected in Asheville. That's what solar looks like now. Apply the solar to that peak, and you might get that on a winter peak day. Of course, it only helps in the daytime, not at night. So let's tie this to this graph. That is that point. That's what it looks like if the solar and the air source heat pumps. Go to the next slide. That's going to be what water tanks will do in a very poor formula. I just did a spreadsheet on that. And that's what that curve is like. You can get those peaks down just with water tanks, like cubes in your basement, you know? And then with adding geothermal, you can get it even much further down, and that's what that curve is. Now you can sort of see why those three are important to understand differently. They vastly affect the winter peak load. They vastly thus affect the pace of decarbonization. So this is basically, I would suggest you never, certainly at the 150, 145% growth across the country, slow growth, but can be done. Fast growth, if you go up to geothermal. That's what, of course, that HRA study did. This will cost a fortune. That will cost a lot. That'll cost a lot less because it's more efficient. And our point is there's another point that's worth looking at. So let's get into that. What is that other point in between those? So this is Dr. Liu at Oak Ridge National Labs has created a battery and has this in test now. Basically, this is like a 20-foot deep, 2-foot diameter kind of bore, 3-foot diameter bore with both water and phase change materials and in the ground. So this creates a 3-in-1 battery that's water, phase change, and a ground battery. That changes the paradigm a lot. And other people have other designs of how you do geothermal to be able to store more energy, recover more energy, affects the efficiency and interactivity of the grid. So they have some other parameters involved in that the storage capacity now varies between this huge capacity in the geothermal and very limited for water, but something tunable in between. And with you get to the other side of this is the bandwidth. So a water battery, you can get that energy out really fast, and that ground battery is really slow because it's an annual battery. These are all design parameters that are involved. Basically, though, there's some battery combination in here that produces a result that's even better. And it's like, that's where we need to discover what these batteries are. They're going to be custom tuned to different locations, different building uses, different power patterns. It creates some ideal minimum cost for overall transformation there on the top and some ideal maximum cost. And our contention is that there's actually, when you start factoring in the 2050 grid, you'll find that there's even another aspect that's not a straight line because you're interacting with that grid and storing power when it's cheap and then not using it when it's expensive. And there's going to be two other points in here. There's going to be lower points even on that operational curve. And we need to find out what those are. So it's all about this. And if you want to understand how to design these thermal batteries and get this designed, there's a lot of factors. This is just some of them. Local weather, of course, your building, a physical site, the technology you're going to use, the capacity you need, the bandwidth you need to be able to deal with the fluctuating power and your buildings, power tuning for that grid, the resilience, which we've not talked about, installation cost, operation cost, and the grid cost. And all that together is going to control the speed we as a society can decarbonize. So this is what we're working on. We got a project underway at MIT D-Lab doing this to learn how to provide a tool for this highly complex design in an En-ROAD style single page interactive simulator that even activists can use to help drive rapid climate action. So again, that's the totality of this. That's what all's involved in this graph and what is needed. Without that software, we're not going to get there. Thank you.